Hey, time for the next lesson, sustainable ecosystems and energy. So, what's a sustainable ecosystem? Well, now that our ship's launched, okay, so in part two, we're basically on a ship and we're trying to get out of the solar system. And we're going to be there for quite a while. Probably, I mean, even if you look at the different ways of traveling, it's probably going to be over a generation, meaning that you won't get there, your kids will. So, every biotic and abiotic factor that can affect us is now enclosed on this ship with us, which creates a really interesting way to look at ecosystems, because you have a completely closed ecosystem that has to be sustainable. So it can't run out of anything before we get to our destination, otherwise the whole thing could collapse. So to understand it, you got to look at energy flow. So we know all energy starts with the sun. We started about that last time, and we know how it starts. It starts with plants. Plants with photosynthesis can get energy from the sun. They're the only organisms that can do that. So they're the start of every food, what we call food chain on Earth. So every possible start begins with the plants, turning sunlight into that chemical energy, that sugar. They also produce the oxygen that we need to breathe. Now, because of that, we call plants producers, because they produce the energy. They don't actually produce the energy, but they produce it in a form that everything else can use. The things that eat plants are referred to as primary consumers. Now, primary consumers only eat producers, okay? We're not a primary consumer, well, unless you're a vegetarian. If you're a vegetarian, you're a primary consumer. If you're not a vegetarian, you're not a primary consumer, because you also eat primary consumers as part of your food. So, primary consumers just rely on the glucose from plants. We call them herbivores, and they're always second in those food chains. Secondary consumers are organisms that eat primary consumers. So they get energy from the fat and muscle in the producers. They're carnivores. Now, we're probably not carnivores either. Some of us are closer than others, but we tend to eat both. So we actually are usually what are called top carnivores, because there are some carnivores that hunt other carnivores. So they hunt other carnivores, they hunt producers, they hunt the primary consumers. Example's a wolf, right? It could eat a raccoon, which is a secondary, or it could eat a deer, which is a primary. So the top carnivores are basically the tops of the food chain. Humans are a specific type of top carnivore called an omnivore. Now, not all omnivores are top carnivores. For example, the raccoon is an omnivore, but it's not the top carnivore in most ecosystems. But it has an advantage in that it can eat carnivore, it can eat plants or animals. So it can eat producers or other consumers, which makes for a lot of versatility, which means good survival. So a lot of larger animals are omnivores because it works. You have a lot of energy. You can get it from a lot of places. Like, so large things like bears, it's how they find enough energy to power an entire bear, is that they can eat plants, they can eat animals, they can eat whatever they get their mouth on. And that versatility makes them for a good survival. The last step we usually don't include in food chains, but are at the end of every food chain eventually, are what we call decomposers. And they're the organisms that break down the dead material, and that's how they get their energy and their nutrients. And they're not scavengers, by the way. A scavenger is a carnivore that eats things that other animals have killed, okay? Decomposers are things that break them down. So worms, fungi, bacteria. We don't usually include them in the food chain, but they're basically connecting the end back to the beginning. They get the nutrients back into the soil, which the plants need to actually produce the glucose. So, how do we do it? Well, we line them up as what's called a food chain. A food chain is a diagram showing the energy through an ecosystem. And we put arrows to show the direction the energy flows. Think of the arrow as flowing, this goes into the mouth of this. This goes into the mouth of this. This is one of the only ways you can get these wrong, is by putting the arrows in the wrong direction and have your mice eating snakes, which is kind of weird. It would be cool to watch, but kind of weird. Not the way nature does it. So, for example, you always start with a producer, primary consumer, secondary consumer, and tertiary consumer, or top carnivore. So in this case, this would be an ecosystem that would work. But what would make it stable? Well, it's what's called a food pyramid. Now, a food pyramid is a food chain that shows how many of each organism are in the food chain. So most of you, I'm going to ask a question like, which one would have to be in the biggest supply? There was actually a question on the test about it. Would you need more scorpions or hawks? Well, you'd need a lot more scorpions because every hawk may eat hundreds of scorpions in their life, but a scorpion can only get eaten once. So a food pyramid is a food chain that shows how many of each organism there are. And as you go up the food chain, you have to have less and less and less so that it's still supported. I actually like the food pyramid because sort of visually it makes sense. If anything gets too small, like if the herring got too small, it would tip over, it wouldn't be sustainable. So for a food chain to be sustainable, the numbers of the animals have to make a pyramid because you can't have more things eating than that have food, right? You can't have more mackerel than herring, otherwise the mackerel are going to starve because they've got no food. So that means for us on the ship, food would be a limiting factor. So here's the math. To feed a person, you need about 50 to 100 square meters to produce enough food and oxygen from plants. So if you're using high-tech hydroponics, you could basically keep a person alive on plants as long as there's 50 to 100 square meters of plants per person constantly. And so if we assume those trays are 1 meter apart, that means for 10,000 people, let's say that's what our ship is carrying, you would need a ship the size of 4 to 6 super tankers just to store the plants necessary to provide enough food and oxygen for the people. And that's not including feeding any animals we might bring with us. That's literally just if you were eating the plants. So food is going to be a really interesting problem for us. How do we get enough oxygen, enough food to feed a large number of people for a large period of time? And that's what's probably going to be, so this idea of food, that we look at in ecology, if you're in a very enclosed ecosystem, becomes really difficult to try and solve. And it's kind of neat that nature does it on its own. All right, that's the end.